In this video, let's explore Numpy Library for data analytics. This is one of the most popular libraries. I would highly recommend that you type the code along with me. Numpy is the backbone for many of the scientific and numerical computing libraries in Python. It is also used in Pandas package, which is one of the most popular package for data analytics and data science. Numpy provides extension to Python data structures. The main data structure for Numpy is arrays, and this is a very efficient data structure compared to Python data structures. Numpy is written in C programming language and it uses vectorization to perform fast calculations on number data types. As we all know that loops can be a bottleneck in any kind of calculations, so it totally tries to avoid that. We will see how it compares to Python data structures once we know how to use it. Now, if we want to use Numpy in our project, we first have to import Numpy libraries. To import it, we can use import numpy as np. This np is the common convention among data scientists and data analysts. Whenever you see np, you can imagine that it's a Numpy library. I would also recommend that you should also use the same alias for Numpy packages. When we want to use Numpy functions, we have to write numpy.sum function name. In order to avoid writing numpy multiple times, we use this short notation for Numpy libraries. Now to create array, we can use multiple methods from Numpy package. We can convert Python sequences into Numpy arrays. We could also create Numpy arrays by loading data from files. There are also special functions in Numpy package which can help us easily create Numpy arrays. So let's see how we can create Numpy arrays. If we have a list with elements 1, 2, and 3, we can create Numpy array with these elements using np.array. In this function, we can pass the list object we have available. So if I pass this list into this function and assign it to a variable a, let's run this code. And now if I check the variable a, you can see that it returns array with elements 1, 2, and 3. If I check the data type for this variable, it returns numpy.ndarray. This is the main data structure of Numpy library. Here ndarray means it's an n-dimensional array. In this case, it's just one-dimensional array, but we can create any dimensional array in Numpy. And that's the main benefit of Numpy arrays. This ND array also provides memory efficient implementation of container data types. We can perform fast numerical operations using this ND array objects. If I want to create multi-dimensional array, then I can pass nested list inside this np.array function. So let's create two-dimensional array, np.array, and in this function I'm passing nested list with elements 1, 2, 3, and 4, 5, 6. Let's assign it to a variable matrix. If I run this and check our matrix variable, you can see that it creates a matrix kind of object. You might be familiar with this matrix objects from your high school mathematics. This looks very similar to two-dimensional arrays. If I want to create three-dimensional array, then I can create array 3D equals np.array, And in this, I have to pass the nested list. So in the first list, I will have two lists. In the inner list, I can have elements 0, 1, 2, 3, 4, 5, 6, 7, 8. And in the second list, I can have elements 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's also verify this array. And now, if I run this cell, you can see that it creates an array with 3 dimensions. Here in the outer list, you can see we have this 2 inner list, and each of them have dimension 3 by 3. We could also check the dimension of the NumPy array using ndim attribute. Attributes are some of the properties we have with specific kind of data type. So if I check our a.ndim, this was the first array we created. It has dimension of 1. If I check the dimension for our matrix, it gives me 2. And similarly, for this 3-dimensional array, it returns 3. Now talking about some of the terminologies, 1-dimensional array is also called a vector. 2-dimensional array is called matrix. And if we have more than 2 dimensions, then it's called a tensor in mathematics. We also have a very popular deep learning library called TensorFlow. So now you know what tensor means. There are many other methods to create NumPy arrays. Let's see them one by one in this lesson. We could also use arange function. This arange function is very similar to range function in Python. So I can create an array, array1 equals np.arange with value 10. So this will create an array with elements 0 to 9. This is exactly similar to how we would have got list with elements 0 to 9 by using range function. Let's verify this, and we can see that it returns 0 to 9 elements in this array. We could also check the shape of any array. So if I try array1.shape, it returns this tuple with element 10. So it is a 1-dimensional array, and that 1 dimension has 10 elements. This trailing comma is the convention for the tuple. Let's get back to our matrix object. We can see that it was 2-dimensional array. If I check the shape for this matrix, it returns 2, 3. So it has these 2 rows and 3 columns. Similarly, let's print our 3D array first. And now let's check out its shape. We get back 2, 3, 3. So in this 3-dimensional array, we have this outer dimension with 2 lists inside it. And both the lists have 3 rows and 3 columns. And that's how we get this 2, 3, 3. We could also use the len function, which will give how many elements there are in the array. So if I check len of array1, it returns 10 because it has 10 elements. If I check the len of matrix, then it has 2 nested elements. If I check the length of a 3D array, this one also has 2 nested elements, with each element being 2-dimensional array. If you want to see how many elements there are in the nested array, then we can use the size attribute. So array1.size, matrix.size, and array3.size If I check all of these, we get 10, 6, and 18. In array 1, we had 10 elements. In matrix, we had total of 2 by 3, 6 elements. And this 3D array, we have total of 18 elements. In Jupyter Notebooks, if we want to check out the documentation for any of the function, we could easily check them by using Shift tab. So let's check the documentation for our arange function, np.arange, and now I press Shift tab. It shows me this inline documentation. If I expand it, you can see little more detail. So this arange function takes start value, stop value, and step value. This is very similar to what we have seen in range function from Python. So we could specify the end value. So let's check that. np.arange 510, and this returns 5 to 9 elements in the array. Similarly, I could also specify the step value. So if I perform array1 equals np.arange 1, 10, and 2, it returns every second element up to 10. In NumPy, there is a special function, Linspace, which creates linearly separated elements from a specific range. So if I write np.linspace 0, 5, and 6, then it will create 6 element array which are linearly separated between 0 to 5. So it will create elements 0, 1, 2, 3, 4, and 5. They are all separated by 1. Here the trailing dot means these are all floating point numbers. It's like 1.0, 2.0, and so on. We will learn about data types later. We could also create an array with all the elements as 1. We can use ones function, and this function needs the shape of the array we want to create. So let's create a 3 by 3 array with all the elements as 1. If I check it out, you can see all the elements have value 1. We could also create an array with all elements as zeros, np.zeros, 3 by 3, and let's check this out. Similarly, I can create an identity matrix using np.I function. This only needs one size because identity matrix always have the same number of rows as the number of columns. For a recall, identity matrix have all the diagonal elements as 1, and every other element in the matrix will have the value 0. So if I check this out, it creates an array with all the diagonal elements as 1. Similarly, I can create an array with only the diagonal elements being non-zero. I can use this function, and I have to specify what elements I want in the diagonal of this array. If I specify 1, 2, and 3, it creates a diagonal array with the diagonal having values 1, 2, and 3. Every other element is having the value 0. To create a NumPy array with random values, we can use the random module from this NumPy package. This can be very useful when you want to sample the data and when you want to create random distribution using this array objects. I can use np.random.rand, and I can specify any value inside it. If I specify 4, it will create an array with 4 values. These values will be in the range 0 to 1, where the last value 1 will not be included in this random distribution. This function generates a random variable based on uniform distribution in the range 0 to 1. If I want to generate a random number using standard normal distribution, I can use np.random.randn. And this generates random numbers based on standard normal distribution. I could also use np.random.randint function, and in that I can also specify the range between which I want to create the integer number. If I write 110, then it will generate a random number between 1 to 10. I could also create an array using this Randint function. So if I specify the range as 5 to 10, and if I specify the size as 4, it will create a random array with size 4. If I check the size, it has 4. I could also create an array with 2 dimensions like this. If I check the shape of this random array, it returns 3, 4. So it has 3 rows and 4 columns. I could also omit the start value in this Randint function, and that will by default create random numbers between 0 to 10. Similarly, I can also use random function from random module, and this only takes the shape tuple. So I can specify 2, 2, and it will create an array with shape 2 by 2. All the values will be in the range 0 to 1. Now all these random numbers are pseudo-random numbers. This means they are not really random. We can set a seed, and that will make sure that it generates the same numbers. Now you might think, why would you do that? This can be useful when you want to replicate the same dataset multiple times. So for example, when you are running some experiment, you want to have the same numbers generated every time. In that case, we can set the seed like this: np.random.seed, and I can specify some value inside this. And now if I generate the random numbers using np.random.randint up to 10 with size 2 by 3. If I run this, you can see that it generates this array, but if I run this again, it generates the same array with elements 5, 8, 9. So that way we can make sure that we are getting the same dataset with random values. If we want to generate 4-dimensional array, which can be very difficult by specifying the list objects, we can use this Randint function. A4 equals np.random.randint with random numbers up to 10, and in the size I can specify 2, 3, 3, 4. If I check this out, you can see this has generated a 4-dimensional array. It would be very difficult to generate this manually. In that case, this Randint function can be very helpful. If I check the shape of this array, it has 2, 3, 3, 4. If I check the size, it has 72 elements. So let's verify that. 2 multiplied by 3 by 3 by 4, and this returns 72. So our size is correct. Now if we want to compare the Python data structure against the NumPy data structure, we can use a magic function from Jupyter Notebook. Magics are the built-in structure from Jupyter Notebook. They are written using %sign. We have magic function timeIt, which can be used to time a specific execution. So we can compare how long it takes for Python data structure to perform some calculation, and we can compare that against the NumPy data structure. So here I want to create a numbers list with double the value of original list. I can use list comprehension for that. I can write I multiplied by 2 for I in range 10,000. And I'm using this timeIt function that will calculate the time for this operation. In NumPy, we can generate an array with 10,000 elements using arange function. A equals np.arange 10,000. Now to multiply each number by 2, in NumPy we can simply use A multiplied by 2. And let's time this execution using timeIt magic. If I run this, and this may take some time, here we can see that Python execution took around 1.11 milliseconds. This was decided based on 7 runs, so this timeIt function calculates the average. Whereas NumPy array took around 10.5 microseconds. This was also calculated based on 7 runs. So we can see that NumPy arrays are almost 100 times faster than Python data structures. This is a dramatic difference between the performance of array data types. Now this video is getting a little bit longer, so let's pause here and we will continue our exploration of NumPy package in the next video. In the next video, we will explore the data types of the NumPy array, and we will also see some of the other functions we can use to create NumPy arrays.